two different homeworks. One is feedforward. So we have transfer functions for G and GD. The feedforward controller should be negative GD over G. But when you formulate that, this numerator, negative 3x plus 4, when you divide by G, that's become the right half plane 0 becomes the right half plane pole. So you have to get rid of it without changing the gain of the feedforward controller. Then it says use these models with the controller you developed in part 1 to do a simulation. So we basically formulate, thinking we have the models for G and GD. We use GD and G in the simulation. So this is the new GD and the new G. We have the measured disturbance, and we have our formulated feedforward controller, which is negative GD over G. So it's a big transfer function, and it's going to be improper. So to make it semi-proper, you have to put a lambda s plus 1 filter in there, at least one, to make it at least semi-proper. So when you look at the simulation, I did 3 different feedforward controllers here with different lambda values. So they're both s squared over s squared with that lambda s plus 1 multiplied in the denominator. When you run this, you can see 3 different responses. A perfect feedforward controller, when the disturbance hits, would push the process back to 0, like the disturbance was totally rejected. Without a controller, the yellow line is without any feedforward control operating. It moves up and doesn't come back at all. There's no adjustment. The input doesn't change at all. But with the 3 different lambda values, there's a slow one with lambda equals 1. Lambda equals 5. There's a medium one with lambda equals 1, and there's a fast one with lambda equals 0.2. So the slow response sees the disturbance, it pushes it back slowly. The medium one makes it a little more aggressive, it changes the input, and then gets to where it should be a steady state. And the aggressive one changes the input very rapidly, very vigorously, to try and get the process to its new steady state value as rapidly as possible. So that's 3 different lambda values. The whole trick is taking negative GD over G to formulate that feedforward controller, getting rid of the time delay if you need to, getting rid of the problematic right half plane 0 that becomes a right half plane pole, and then fixing it with lambda s plus 1, where you get to pick whatever lambda s plus 1 is. Yeah, different. You can play around with that with the simulation, or you can put it on the order of the transfer function, time constants in the process. The other problem we have done is IMC. So IMC, I give you the process, the disturbance, and the process. In this case, the process model is a 4th order system. For IMC, you have the process disturbance and the process itself, the process running in parallel. So these two actually match. If we assume the process and the process model are identical, we determine the disturbance here. It's basically an inferred disturbance. So any difference between the real process and the process model is attributed to the disturbance here. Using this process model, we invert it to make the controller 1 over G. But in this case, when you invert it, you have a right half plane 0. It becomes a right half plane pole when you invert it. And it looks like when you invert it, you have a 4th order system you're inverting, so it's going to be a 4th order system. The denominator needs to be 4th order. So you have 6s plus 24 in my example. But then you have to have lambda s plus 1 3 times, and using convolution function, you can multiply that through. Numerator is actually multiplying a 2nd order polynomial on a 2nd order polynomial to get the 4th order polynomial there. So it's using this convolve function where you multiply 2 polynomial representations together. This one I'm using convolve like 3 times. Multiply those 2, and then take that and multiply it by that, and then take that 3rd order polynomial and multiply it by this 2nd order or 1st order polynomial to get a 4th order. And with different values of lambda, you can run this and see the response. So this, I think my lambda value is 0.1 in this case. So with a lambda of 0.1, you can see that it's a pretty rapid response. The input moves very aggressively. It tracks the set. This is the y up there. The set point changes in the process response. There's inverse response in the process, which is what we expected because we had an inverse response here. And when there's disturbance, the process is pushed away and it set point. I ran 2 of these, so 2 different lambda values. One is more aggressive than the other. So you can see that one is aggressive and one is a little slower. You can change that lambda value. Rerun the simulation. And just slows down the simulation. So it's not as much aggressive movement. When you have there's no model mismatch in this, there's no noise. There's a set point change in disturbance. So this is the ideal IMC system. So this is the best system. Whereas on the feed-forward system, we had built in a change in G and GD. We changed out the process model so that it wasn't an ideal system. The 2 models are slightly off, so the feed-forward is not perfect. The IMC is about as good as it can get in this case. In reality, you have limits on the input actuator, so you couldn't spike the valve position as fast or as rapidly as you really wanted to. You have noise, you have model mismatch, you have nonlinearity. So these responses are idealized. And you can push it about as hard as you want to. If we change lambda to something like very small, and we run this, it's going to be a very aggressive attempt to invert the process. You're going to get an input that's actually too far. So it's trying to invert the process perfectly. It's trying to make the process stay at the set point perfectly. I think I drew it a little too far in that case. Let me back that off and order of magnitude and see what happens when we run it again. A little better, but you can see that the valve now, instead of going up to like 10, goes up to 10,000. It's still pretty aggressive. So that lambda filter is the degree. Bigger is slower. So if you make it small, you're trying to invert the process perfectly. You're trying to get exactly the set point. You see a set point change, you're trying to get it. You see the disturbance pushing you away, you're trying to push it back as hard as you can. So that is the distinction between these.